for our lab example, we have our data table here. And we have our length of magnesium ribbon, which was 3.5 centimeters. We've already calculated our mass of the magnesium ribbon was 0.022 grams. And we have found the volume of hydrogen to be 23.10 milliliters, and that was all at 20 degrees Celsius. And we have a barometric pressure reading of 765 millimeters of mercury. Alright, so that's the data that we're given. We're also told that at 20 degrees Celsius, the partial pressure for the water is equal to 21.1 millimeters of mercury. Cam's trying to call me while I'm working on this. We also know that 1 atmosphere is equal to 760 millimeters of mercury, and 1 kPa is equal to 75,000 millimeters of mercury. So we can make all the necessary conversions. So in A, they want us to use the mass of the manganese to calculate the theoretical number of moles of hydrogen gas produced. Now, this reaction is pretty straightforward because it's Mg plus HCl. Single replacement, right? So the magnesium comes in, kicks out the hydrogen. We end up with H2 being produced plus the MgCl2. The reason it's MgCl2 is magnesium is a 2+ charge, and Cl is a 1 negative. So in order to get this to balance, it's actually a 1:2 ratio between the magnesium and the hydrochloric acid. For A, though, that doesn't really make that much difference because we're just trying to convert we don't even need this last step actually, because we want to know moles. I'm off the screen. We just need to know moles of H2. So to set that up, we have to start by converting out of grams. So we need the formula mass off the periodic table of magnesium. Then we're converting from magnesium to hydrogen, and that is a 1:1. If you look on here, that's a 1 and that's a 1. So in order to do this conversion, we divide by 22.3, multiply by 1, divide by 1, so that does nothing mathematically, and we get 9.05 times 10 to the negative 4 moles of H2. All right, in B, we use the partial pressure to figure out the pressure of just the hydrogen. Okay, the way that works is you take your total atmospheric pressure, or P total, and you compare that to the pressure of the water and the pressure of the hydrogen, because all those should add up to be the 765 millimeters of mercury. And we know that the water is 21.1. So that means X is the amount for the hydrogen, okay? So it's 765 minus 21.1 to figure out how much pressure is derived from the mercury. Sorry, not the mercury, the hydrogen. So that for B, 743.9 is your pressure of just the hydrogen. All right. In C, use the combined gas law to find the volume of the gas that will occupy at standard conditions. So we've derived this a bunch of times. I'm just going to write down the way that we use it because we're looking for a new volume here. So just the same as we saw before. It's P1 V1 T2 over T1 P2 to solve for the new volume. And because everything is in millimeters of mercury, we don't really need to convert any of that because it will just cancel out. Now it was 23.1 milliliters, so you have to divide that by 1,000 to get the volume to be in liters. It does have to be in liters for this to work. Temperature has to be in Kelvin. That's standard conditions. This is actual conditions at 20 degrees Celsius. And that's standard conditions for the pressure. So that gives us 0.0210 liters per C. Alright, which is pretty close to, 2022, but we need to find, I know, we need to find the molar volume real quick. So molar volume is equal to liters over moles. And we currently have 0.0210 liters, and we have 9.05 times 10 to the negative 4 moles, which gives us 23.2 liters per mole. Yeah, I know. How far off is that? Percent error is equal to the 23.2 minus what it should be divided by what it should be times 100%, which is 3.59%, which is very good.